This is question 3 from the 2018 AP Physics C Mechanics FRQ. So the problem states, using integral calculus, show that the rotational inertia of the rod about its left end is ml squared over 2, where we are rotating a triangular piece with length L and non-uniform density described by the equation 2m over L squared times x. So let's start by writing our equation for the moment of inertia. I equals integral r squared dm. So replace r with x equals x squared dm. And then recognize that this is the equation for the non-uniform density is giving us lambda equals dm over dx. So for every little bit of mass and every little bit of x that we go, that's going to give us our density at every point. So if we multiply by dx on both sides, we get lambda dx equals dm. And we can substitute that into our equation to get integral of x squared lambda dx. Now we're going to want to substitute lambda for the equation we derived to get equals x squared times 2m over L squared times x dx. Now let's plug in our limits of integration. We are integrating from x equals 0 to x equals L because that's the length of the rod. So x equals 0 to x equals L. Let's simplify and move our constants outside of the equation. So now we get integral from 0 to L of 2m over L squared x cubed dx. Evaluating this integral, or taking this integral, we get 2m over L squared times x to the fourth over 4 minus L to the fourth minus 4 minus 0 to the fourth over 4. So this doesn't matter, and then we get 2m L to the fourth over 4 L squared. We cancel the 2 to get 2 up here. Cancel this, and we get 1 over 2. So this does, in fact, end up equaling ml squared over 2, as we're trying to find in the problem statement. Continuing to part B, we are now given a circular ring with mass I, radius L, moment of inertia I equals ml squared, and we are given that same, and inside of that ring, we now have the 3 triangles we found from part A, and we are asked to derive an expression for the total rotational inertia of the hooped rod system about the center of the hoop. So we're going to be expressing this in ml and any physical constants as we would expect. So as we can see, because the left side is what's facing in, we do not have to use the parallel axis theorem, and we can actually just directly use our knowledge of moment of inertial equations to say the sum of the moment of inertias equals I total. So we just have to say, okay, ml squared plus one of these, so plus there's 3 triangle rods, and we determined in the previous that the moment of inertia was ml squared over 2. So this equals ml squared plus 3 over 2 ml squared equals simply 5 over 2 ml squared. And that gives us the moment of inertia. Question C tasks us with finding the final angular velocity of the system after force F is applied tangentially for delta time t in terms of mf delta t and L. So let's start by writing the equation for torque. Torque equals moment of inertia times alpha, the angular acceleration. So we know that torque also equals F times R, which in this case is L, because that's the radius. And from our previous problem, we know that I, moment of inertia, equals 5 over 2 ml squared. Plugging in, we get F times L equals 5 over 2 ml squared times alpha, dividing both sides by this quantity, 5 over 2 ml squared. We get alpha equals F 2F over 5 ml. Now we know that from our kinematic equations, omega final equals omega initial times alpha t. So omega initial is going to be 0 because it's thought at rest, and t is going to be delta t. So we find that w or omega f equals 2f delta t over 5ml. Now we're at part D. The system has been rolling along a horizontal surface. It gets to a ramp, and with non-slip conditions starts rolling up the ramp. We are at task to draw and label forces on the system and justify those forces. So the only forces we're going to have is going to be the normal force, which is going to always be perpendicular to the axis. We then will also have weight, which is always going to be straight down. So it's mg. And then we are also going to have, this is m system g, but we're also going to have the frictional force. Now, if the system is rolling up the hill this way, it is going to be rotating this way. That means this point is going to be going this way. That means friction is going to be the opposite direction, up the incline this way. So this is our frictional force. So justifying exactly what I just said, the normal force is perpendicular to slope. Then we also have that weight is always down, and friction is parallel to slope in opposite direction. So that is our answer. Part E, we are asked to analyze the same situation, but now we're asked to derive an equation for the maximum height it reaches with the variables m, l, the total moment of inertia of the system, the angular velocity, and physical constants. So let's use a energy analysis here. So m, I'm going to write lowercase m because this is of the entire system. M g h max, we know, is going to equal 1/2 the rotational velocity. So 1 squared times the moment of inertia, plus also the translational velocity, 1/2 v squared times m. And now we are going to look at this again. We're going to convert v into w. So because it's non-slip conditions, we can say that v equals w times r, where r is going to actually be L. So now we're going to say that mgh max equals 1/2 omega squared. I might have said w earlier, I'm really sorry. Times I total, I'm very total here because that's what it is. Plus 1/2 w squared times L squared times m. So let's find what m equals. M is going to equal the mass of these three, which is 3m, and the mass of the entire ring is 1m, so 3m plus m equals 4m equals small m. So let's write that in. 4mg times h max equals 1/2. Let's factor out the 1/2. Let's factor out the omega squared. I total times L squared times 4m. So now we can divide both sides by 4m, and we get h max equals, this is going to cancel a bit, so we're only going to have, actually no, it's going to multiply together, so we're going to have 8m on the bottom, omega squared times I total times L squared times 4m, all over 8mg. And that is going to be our final answer for the maximum height that it reaches.